Tech, advised by Richard Murray. He obtained his PhD at Berkeley in 2022 under the guidance of Professor Alberto Sangiovanni Vincentelli. And he's interested in all aspects of cyber-physical systems, emphasizing formal methods and AI that supports their compositional design and analysis. And today with us, we'll talk about system analysis and design under assumed guarantee contracts. So thank you very much for being here today, and the floor is yours.
Thank you so much, Nicholas, and good afternoon, everyone. I am delighted to be with you today and have this conversation about system design and what we have been doing regarding the use of contracts in order to do this. In order to talk about contracts, I think that the right, we could say, ecosystem, in which they find their natural role is that of systems engineering. So it is informative, in my opinion, to take a look at the origin of this field. And it turns out that the first systems engineering department in an academic setting was established at the University of Arizona in 1960. So Professor Wayne Wymore, whose name is on the slide, was the first chair of such a department. And it caught my attention that, in his autobiographical notes and his recollections about this time, Professor Wymore talks about a time when the dean of his college came to talk to him, and Wymore recalls approximately the following words from his dean. So the dean said something like this: I just returned from a meeting at the American Society for Engineering Education, and I heard of this new exciting discipline called systems engineering. So the dean said, remember, this is 1950 something, right? Late 1950s. It is no longer sufficient, for engineers merely to design boxes with the hope that they are going to become components of larger, complicated things, right? So we have to learn how to design large-scale complex systems from the top down, so that the specification for every component can be derived from the requirements of the overall system. Okay, so this focus on specification-based design has been with systems engineering from the get-go of the field. So a few years later, if we take a look at an influential systems engineering textbook from the early 90s, by Derek Hitchens. Hitchens claims that if you talk to most systems engineers, they will tell you that their field consists at a high level from the following steps. So the first step is you describe your system at the most abstract level. Second step, you decompose requirements functionally. Then you map the decomposed requirements to an architecture. And finally, you develop physical elements and you integrate. So what I found remarkable about these 4 steps is that 3 out of the 4 steps have something directly to do with specifications. Right? So specification is central, right, to system design. And it is not surprising that they appear so often in every single survey that I have seen of system engineers talking about the top challenges in their field. You see requirement engineering appearing in the number 1 or number 2 spot. So, requirements can be conflicting, they can change as customers react to market conditions and so on, right? So something that academia has done in order to reply to this challenge with requirements has been to formalize them, right? So if we say, okay, if we give mathematical meaning to requirements, then we should be able to carry out analysis on them and so on. And this is the context, would say, in which we have this object that we call contracts. So contracts at a high level are going to be formal specifications that we split in 2 pieces. So first we state what are the expectations that we have on the environment, and then we state what are the responsibilities that we are going to assign to the object of interest when it operates in an environment that meets the assumptions of the contract. So this is exactly the notion of a datasheet. The datasheet will tell you this is what your component can do, provided that you meet certain requirements, that your temperature is bounded by certain numbers, that your input voltages are bounded by some ranges, and so on. So in contracts, we have 2 things. We have an algebra that we will discuss soon, but we also have a methodology that allows us to do several design relevant tasks. So the first task that we have at hand is the one of system integration. What we mean by system integration, right, is this idea of building complicated objects out of components and simpler things. So this is system integration. In system integration, we have this notion of components coming from multiple vendors, And we want to understand the specification of the system from the specification of the pieces that compose the system. We are going to have an algebraic operation in the theory called composition that is going to generate the system spec from the subsystem specifications. Analogously, we have an operation that allows us to undo composition, okay? So this notion of quotient that we will define soon is going to be an operation that allows you to do the following. You say, I want to build a system that with a certain objective, and I have a piece that I already designed, and I have the specification for the piece that I designed of my system. So the quotient tells you what is the thing, what is the specification of the thing that you are missing, such that your system satisfies its objective. Okay? So that's what we mean here by system integration. So this is something that contracts will give us, and contracts also have something to say regarding the handling of viewpoints in system design. So by viewpoints, in this sense, we mean the following. At the same company, there can be multiple groups working on the same design element. Okay? So these multiple groups can be focused on various aspects of this object. So there can be a group that is focused on generating a functionality specification. There is another group that may be in charge of generating a performance specification, as in power or timing and so on. So the algebra should also give us ways to handle these multiple aspects that apply to the same object. And we are going to define this object soon. So that being said, these are more or less our topics for today. So, first we are going to be looking at some preliminaries of assumed guarantee reasoning, and that is behavioral modeling. Then the second or the first main topic that I think would be important for us to discuss today is that there are actually a total of 8 operations in the theory that have design relevant applications. So this is one of the main topics, the operations on assumed guarantee contracts. The second topic that would be good for us to discuss too is the fact that there is a tool now that allows us to carry out this specification-based design automatically. So these algebraic operations have been implemented, and we are going to be taking a look at some examples of the use of this tool. But before we discuss contract operations, we are going to say a couple of things about behavioral modeling. Behavioral modeling is the mathematics on which contracts rest. So we should take a look at what that is. So behavioral modeling, it's we could say a modeling philosophy, right, in which we think of components as the set of behaviors that they can exhibit. So we take a fairly abstract view of components, right, here, and we simply say that, we happen to have access to an abstract set calligraphic B, and the elements of this calligraphic B are going to be called behaviors. By making that statement, we have already made the decision that all modeling aspects of the design have already been taken care of. Okay, so I want to make that clear in the sense that assumed guarantee reasoning will add 0 to our modeling capabilities of components. But assumed guarantee reasoning starts making sense after we have decided how much detail we want to have in our description of the components that we are using, right? So if we only care about static values in our system, right? So static behaviors will be sufficient, right? If we only care to say about, if we only care to make statements like the voltage is never going to exceed a certain number or the temperature will never be outside this value, our modeling framework, our sets of behaviors is going to only include static objects. If we care about dynamics, of course, we need to include functions of time and so on. But in this sense, we defined a component as a set of behaviors. So it is just an element of the power set of B. And behavioral modeling has, we could say, supporters in many fields. So in the case of control, there is Jan Willems, for example, who advocated the use of behavioral modeling. He has a paper with a section titled "The Behavior is All There Is." So, very, very much insistent on this notion of behavioral modeling. In systems engineering, we have people like Wayne Wymore that we mentioned earlier. Professor Wymore was the first chair of a systems engineering department in an academic setting. And in computer science, this is absolutely standard, right? So in computer science formal methods, we always think about procedures as the set of traces that you can witness from them. So that's what a component is. A component is a set of behaviors. A property is also defined as a set of behaviors, okay? The difference between component and property would be semantics. So in the case of a component is the behaviors that that component can display. A property is a set of behaviors that for one reason or another we like. So these are the safe behaviors or the secure behaviors and so on. So this gives us immediately a notion of satisfaction of a property by a component. So we say that a component satisfies a property when every behavior of your component is a behavior that we like, a behavior that is safe and so on. So we have this notion of subcomponents as well, right? So we say that a component is a subcomponent of another one when all its behaviors are contained in the next component. So this is just subsetting. And the last interesting notion in this quick overview is this notion of composition for behavioral modeling. In behavioral modeling, anytime that we take component M and M double prime, and we wish to build a system out of those two objects, we simply have a set intersection. Set intersection of the behaviors is equivalent to ensuring that both components have their constraints on their behaviors simultaneously enforced. Something that is noteworthy about behavioral modeling is that there is only one notion of composition, which is independent of the topology of the composition. So whether we are doing sequential or feedback or any sort of composition is absorbed in this definition of intersection. And that happens because the topology of the interconnection is embedded in the definition of the component. So every component knows what its variables are. Okay? So when you take set intersection, you enforce the constraints that both impose on the behaviors, and therefore the topology is fixed. So this is the notion of composition, and that was our preliminary discussion. Okay, so just what we need in order to define assumed guarantee contracts and their operations. Now we are going to define these objects and see what we can do with them. So regarding questions at any point, please let me know if anything, but would need if it would be helpful to discuss anything further. But now we are going to start defining assumed guarantee contracts. So this slide is going to read as a sequence of definitions, but I think you will agree that they are very intuitive definitions. Okay, so our first definition is this notion of a pre-contract. So a pre-contract is an object that simply takes two properties and puts them together. So we have a property A and a property G. The A is going to stand for assumptions, and the G is going to stand, of course, for guarantees of our object. So this is we could say a semantic-less definition. We are simply taking two properties, putting them together. We have not talked about meaning yet. The next definition is going to add meaning to these objects. So we say that a component E is an environment for the pre-contract when that component satisfies the assumptions of the contract. Okay, so if the contract says, I assume my temperature is less than 100 degrees C, the temperature is 30 degrees C, we are in a valid environment. We say that a component M is an implementation of the contract when the following happens. When the component in question satisfies the guarantees anytime that you make it work in a valid environment for the pre-contract. So there is an asymmetry between environment and implementation, right? In order to be an environment, all you have to do is to satisfy the assumptions. But in order to be an implementation, what you have to do is to satisfy the guarantees, but you can get help from the environment. So this is the definition of an environment and implementation. And again, I think this is very intuitive from datasheet-like objects. So the datasheet tells you this is what the component does, provided that you make it work in an acceptable environment. Now that we have this semantics for the notion of a contract, we can define an equivalence relation, of course. We declare two contracts or two pre-contracts to be equivalent if they have the same environments and the same implementations. So this shouldn't be surprising. And the last definition that we have in this slide simply defines a contract in the following way. We take a pre-contract and we enforce an additional constraint that picks one element from each equivalence class defined by the third definition that we stated. Okay, so I would admit that the only reason, or the main reason, we introduce this last definition or this last constraint in the definition of a contract is because the algebraic presentation of operations is greatly streamlined by this additional constraint, but we are not losing generality by any means. Okay, so now this is our definition of a contract, A, G, with this additional constraint. If you read the literature of contracts, this tends to go by two names. Some people call this constraint the saturation condition, and other authors refer to it as a contract in canonical representation. But now that we have our object, we are going to do the following. We are going to discuss the notion of order and several operations that we have on contracts. So that being said, we are going to take a look at operations and order. The first operation that is interesting in assumed guarantee contracts is an operation that goes by two names. Some authors call it mirror and others call it the reciprocal operation. And what it does is it takes your A, G and it flips them. So this is called mirror because this gives you the specification. The interpretation is that it gives you the specification that the environment has of a component, right? So it is the external view, we could say, of a component. You know, you assume the guarantees and you guarantee the assumptions. The reason this operation is interesting is that it brings a great deal of algebraic unity to the theory. And the way that it does it is as follows. If you have two binary operations on contracts, so suppose that you have operation circle and operation diamond. We are going to call those operations dual when the following happens. You can get the reciprocal of circle by applying diamond to the reciprocal of each of the two contracts. So this is, we could say, very similar to the Morgan's rules in Boolean algebra, right? In which you do negation of conjunction and you get the disjunction of the negations and so on. But we are going to see very soon that this notion of duality appears all over the place in the contract algebra. So this is our notion of reciprocal that is going to show up very soon. Okay, let's talk about order for contracts. Order is very important because it allows us to tell when a specification is stricter than another, right? And the way we defined order for contracts is as follows. Suppose that C and C prime are two contracts that we want to compare, okay? So we are going to say that C refines C prime, or that C is a stricter specification than C prime when the following happens. If you give me an environment for the more relaxed specification, that guy is also an environment for the stricter specification, okay? Conversely, if you give me an implementation for the strict specification, that implementation should also work for the more relaxed specification. If we translate that into the A's and the G's, refinement looks like this. Now, C is a refinement of C prime when the G's go in the same direction as the contract refinement and the A's go in the contravariant direction, right? Than the refinement direction of contracts. So I think this notion is very intuitive, right? So talking about the environments being contravariant and implementations being covariant. What this notion of order generates for us is two operations immediately that are very useful in design. So we are going to talk about these two operations generated from order. And of course, they are going to be the and the or of the theory. So using the notion of refinement, we can get the greatest lower bound, which is the mid of the lattice, and the least upper bound. The closed form expressions are shown on the right-hand side of the slide, right? So this is the way in which we would compute them. But the question is, you know, what is their use in design? So let's talk about what is the role as we are actually using contracts. The conjunction operation, also the meet operation, also called the meet operation, is used as a lossless summary of contracts. Let me explain what I mean. Suppose that C is the specification of the functionality of a self-driving car when it is daytime. And C prime is the functionality of our self-driving car when it is nighttime. So these are disjoint environments, and we have a specification for nighttime, we have a specification for daytime. When we take the conjunction of those two specifications, we get a single specification that remembers what the vehicle has to do at daytime and what the vehicle has to do at nighttime. So this is a complete summary, we could say, of the two specifications. Nothing is lost when we take the meet of the two contracts. So we tend to make use of this operation in order to break, we could say, specifications in disjoint environments. When we want to focus on certain ranges of our environment, right? Say, for example, we want to analyze what we just discussed, the good visibility behavior and the low visibility behavior of our car. This operation allows us to do that. So this is the meet. The join of two contracts is used in order to find shared functionality between specifications. So this is the situation. Suppose that we are Volvo, and Volvo happens to have a family of sedan vehicles. Okay, so they happen to have multiple vehicles. Each of these vehicles comes with its own specification. So you have specification C for sedan 1, specification C prime for another sedan vehicle. When we take the disjunction of those two objects, we get the specification of the functionality that they share. So it's something, we could apply this to a family of products and obtain the functionality that everyone has in the family. Okay. So we already mentioned what conjunction is used for. Conjunction tends to go by the name of weak merging as well. We are going to contrast this with the notion of strong merging that will come in the next couple of slides. And this is the first appearance of this notion of duality that we were discussing earlier. Okay, so conjunction and disjunction are duals of each other. And we have this diagram that we are going to populate as we continue our discussion. So these were the two operations that are generated from order. Now we are going to talk about operations that are defined by axiom in the theory. And the first operation defined by axiom is the notion of composition. So composition is going to be, I would say, this is one of the most important operations in the theory, because composition allows us to build systems out of subsystems, okay? And the definition goes like this of composition. If you take two contracts that are being composed and you build a system out of implementations of the contracts that you are composing, the resulting system should be a valid implementation of the system specification. Okay? So the slogan is that composition of implementations should be an implementation of the composite spec or the system specification. This is part one of the axiom. Part two of the axiom says that if you take an environment of the system specification and in that environment you drop an implementation of one of the contracts that you are composing, the resulting object should be a valid environment of the other contract that we are composing. I tend to refer to this axiom as the Abadi-Lamport composition axiom because it was stated for the first time in about 1993, I believe, in a paper by Martina Bari and Leslie Lamport when they were considering this composition of assumed guarantee specifications. What we typically see in the contract literature is this closed form expression. Okay, so if you have contracts C1 and C2 with assumptions and guarantees, if you want to build a system specification from those two subsystem specifications, this is your closed form expression. Okay, in my opinion, in order to obtain intuition about this, one has to go to the axiom, but we can prove that, that this is a correct instantiation of that axiom, right? In any case, composition is the operation that allows us to build systems out of subsystems, right? So this was our one operation introduced by axiom. And the last operation that I would like to mention regarding assumed guarantee contracts, of the basic operations of assumed guarantee contracts, is something that we call merging, okay? So merging works as follows. There are situations in engineering design when the following happens, okay? Suppose that we are building a PCB and we are going to use somebody's component. So maybe some integrated circuit that somebody developed, okay? In order to use that integrated circuit in our PCB, typically as engineers, we want to make sure that we have everything. We want to make sure that we have timing guarantees and that we have functionality guarantees and power guarantees and so on. Therefore, if your integrated circuit has a specification for timing, a different specification for functionality, a different specification for power, we want the specification that makes sure that all guarantees hold, but we are going to make sure that we provide the assumptions of every viewpoint specification to our component, okay? So this is what is called strong merging. The two assumptions hold, meaning, and as a result, the two guarantees are going to hold, okay? We tend to use this merging operation in order to bring multiple viewpoints together. And in practice, we have found it to be quite useful to do this, right? And this is another appearance of our duality relation. It turns out that the notion of composition and the notion of strong merging are duals of each other. So now our diagram of contract operations looks as what we have in the slide. So two operations come from order, they are dual. Two operations come by axiom, and they are dual. The diagram that we see on the right-hand side of the slide is what we can call the category of assumed guarantee contracts. So in this category, objects are contracts and arrows are the partial order relation. So this is how everything is ordered in this category. So at this point, we have talked about 4 basic operations on contracts, right? So we talk about viewpoint merging, about system building, and so on. The next point that would be important to make is the following. Composition is an operation that allows us to build a system. A natural question is there a way of taking systems apart? Can we optimally decompose specifications using this theory? And we are going to take a look at what this looks like in the theory of assumed guarantee contracts, okay? So we are going to see this, a class of operations that are the categorical adjoints of the operations that we just discussed, and that allows us to do this optimal decomposition. So our first operation goes by the name of quotient. Some authors in the literature also call it residual, but the story is as follows of this notion of quotient. We begin with 2 specifications, C and C prime, okay? C is going to be the specification of the system that we want to implement. In other words, suppose that C is the specification of a car that we want to build. C prime is the specification of a component that is available to us. Say, for example, we already designed the engine of the vehicle. The quotient is going to give us the specification of what we are still missing in order to implement our top-level system. So the definition goes like this. Given contracts C and C prime, we are going to define this object, C divided by C prime, called the quotient, in the following way. This is going to be the largest C double prime with the following property. If you compose C double prime with your existing specification, the resulting object is going to be stricter than what we want to implement, okay? So if we write a first order formula for this, this is what it would look like. If you give me any C double prime, which is a solution to our problem, by our problem, what I mean is a specification that composed with what we have refines the top level specification, okay? So if we obtain a solution C double prime to our problem, that object is a solution if and only if C double prime is a refinement of the quotient. So the quotient has this universal property of being the optimal solution, okay, to our problem. And this diagram simply gives this categorical adjoint description. Up to this point in our development, we don't know whether such an object exists, right, or whether it is unique and so on. But indeed, it is unique and it exists and is unique. It's always defined. Okay, so we can always compute this in a closed form expression. And again, we have found this operation to be quite useful in order to find these missing objects, right, as we are building systems. So up to this point, this is what our diagram looks like, okay, regarding contract operations. There are 4 basic operations, and there is one operation which is a way of undoing composition, right? Just to make the long story short, we are going to say at this point that we know how to optimally undo all the 4 basic operations. So quotient is the right adjoint of composition, separation is the left adjoint of merging, and we also have implication and co-implication that are adjoints of the 2 original operations. And as we said earlier on, this notion of duality ties everything together. So there is there are 8 operations and 4 dualities between them. Regarding our summary, in this table, what we have are the closed form expressions for all the contract operations. So we know how to compute them in a closed form. So at this point, we have a relatively, we could say, would I say drastic, but we have a change of topic. Now we are going to be looking at software in order to implement some of these operations. So if there are no questions, we are going to proceed to discuss software. Okay. So
I have a question. Oh,
okay.
Somebody spoke first. So I understand. I think I understand the high level stuff, but I'm a bit unclear about the first definition that you gave when you said we're going to look at behaviors and then behavior is a set, and then we're going to define a property as a subset and also a component as a subset. But now I struggle a bit about trying to understand what it could be, right? Because if I take, one component, like a battery, like the thing that the battery can see are just, it's a set, which is, the traces of voltages and current or something like that. But then I put a camera, and the camera has, it sees different things, right?
Right.
But you define composition as really like operations on these sets A and G. So I don't see what exactly is this B set.
Okay, understood. So when we took a look at this behavioral modeling, what we said was that behavioral modeling is what we could call the mathematical foundation on which assumed guarantee contracts are built, right? So let's take a look at your example right now. So you're talking about 2 components. One component is a battery with currents and voltages as in its scope, and then there's a camera that has other sort of input and outputs. So in this, when we defined at the level of behavioral modeling, when we define this abstract set B, we are thinking of a universe of behaviors that knows about voltages, currents, and whatever the input and output of your camera is, okay? So let me give you an example. The definition of your battery, suppose that your battery has an extremely simple definition, like it gives you a voltage equal to 5, that's it. So it doesn't care about anything else. So voltage equal to 5, right? Now, the definition in behavioral modeling of your battery would be, my voltage is equal to 5 independently of the image that the camera is seeing. In other words, the set of behaviors represented by the battery component would be 5 cross product the entire set of images, because your battery doesn't care about the images.
Mm-hmm.
Does that make sense? So
basically you're saying that this is not like a bottom-up thing, right? Because essentially when I define a component, I need to refer to a set B, which could be arbitrarily large, right? It contains not only what I care about, but everything else in the world that could be connected. Okay.
What you're saying is absolutely correct, but let me add a little bit of a twist there. That the presentation that we are discussing here regarding behavioral modeling, it's a completely semantic definition. Because it is semantics, we talk about this set as having a universe of behaviors. Now, when we use this theory, nobody is going to write a set by hand, right? You are not going to open curly braces and write all possible behaviors. We use syntax. Now, the syntax of the logical formalism that we use in order to express the specifications tends to be invariant to the other variables in the system. For example, the syntactic representation of your battery is going to be voltage equal to 5, no matter what. However, the semantics of voltage equals to 5 is going to change with the universe of behaviors that you are dealing with. Does that make sense? So, so in the sense that the representation V equals to 5 for the 5 volts of the battery is portable and independent of the other variables, but the set is not. Right? So I know that there is a tension. There is a tension between semantics and syntax here. What we have discussed up to this point has been completely semantic, but in fact, we are going to start looking at syntax in a couple of slides from where we were. But does that make sense, Andrea?
Yeah, it's just unusual. I think I've never seen this, that basically you define things by subtraction. Like, of all the things that could happen, actually, for what regards my variables, only these could happen. So I guess this a component if you just doesn't say anything about anything and just means like whatever, doesn't do anything, right? That's just where like B equal B, that's the, yeah. Okay.
Exactly, you don't do anything. That's exactly right. So, and then, a way that I like to interpret this is that, in this case, think about contract composition, component composition. So we are taking the intersection of behaviors. Intersection of behaviors is the same thing as taking union of the constraints. So suppose that M is your battery of 5 volts and M prime is your camera that has some specification phi. So when we take the composition of these two objects, the syntactic representation of the system is going to say voltage is equal to 5 and phi, whatever constraints come from the camera, right? So then let's see, this appends the constraints that all the components are bringing. Mm-hmm. So, okay, so then you had an important question also regarding the connection between this and the contracts, right? So it is right here. So contracts are defined as A, G, where the A and the G are properties P. Right? So we are thinking of A and G as being also sets of behaviors. All the system level operations that we discussed regarding contracts were given with respect to A and G being as sets of behaviors. But we are going to, when we start talking about software, which is in the next slide, we are going to be using syntax in order to represent this. Mm-hmm. Does that make sense?
Yeah, very
okay.
Very novel. So I'm very curious now about the rest.
Okay, great. So that being said, is it okay if we continue with the software part?
Could I ask a question? Is the notion of an environment for a component a fixed thing, or does the inclusion of other components change the environment for that component? Our components, most of our systems, we end up with multiple components. Do you think of the other components as changing the environment for a given component contract? Absolutely.
So in the sense that if we think about the definition of what a component is, of what an environment is for a contract, it is a component that satisfies the assumptions of the contract. That being said, when you have multiple objects in your system, then the composition of all of those objects should satisfy the assumptions of this contract in order to be an environment. So what you're saying is absolutely right.
Thank you.
Okay, of course. Okay, now that we talk about operations, let's go to a way in which we could use them with the technology that is available right now. So if you go to pacti.org, this is a project that was made public in the last couple of months. And the objective here is to provide a platform, right, that allows us to programmatically compute these operations that you saw, right? And this was done with a wonderful group of collaborators who are experts on various design subjects. So let me tell you a bit about Pacti. So Pacti, by the way, is a Latin word that approximately translates to agreed. So Pacti is aimed to be a tool to enable specification-based system analysis and design. The inputs that we provide to this tool are going to be assumed guarantee contracts in the form that we discussed. We will see examples very soon. The kind of outputs that we can expect to get from Pacti are two things, either new specifications or judgments. Judgments means tell me if a specification is a refinement of another specification. Okay. So, okay, tell me whether a contract refines another, and Pacti will compute contract operations. So you give it, for example, specification of subsystems. You want to build a system out of those objects. It will tell you where the system is. It also has an application to finding bugs from specifications. So the objective was to be efficient. So Pacti was really aimed, to enable design space exploration using specifications. And in order to do this, efficiency was a main concern. We can go straight to some examples now in order to see how we envision specification-based design being used. Okay. So for the first example, we are going to be building a system out of subsystems. So the situation looks as what we have in this diagram. You have two components. You have component M and component M prime. Okay, so component M has input I and output O, and component M prime has input O and output O prime. Could someone please confirm that you are seeing my screen? I got some splashes. Thank you. Thank you. And we have two. Thank you. We have two specifications for our components. The specification C applies to M, specification C prime applies to M prime, okay? So for the first guy, we are saying the following: as long as the input is less than 2, the output is going to be equal to the input. So that's the guarantee, right? And when we go to M prime, we are saying, as long as the input is less than 1, its output should be equal to the input. So it would be nice if we can take about 5 seconds to answer the following. Okay. Suppose that somebody asks you, given these specifications, tell me what is the specification of the system. In other words, if I draw a box around M and M prime, and the only thing that you get to see is I and O prime, what specification would you tell that person that the system has? So somebody wants to use your system, right? So, what is the specification for the resulting object? So what kind of assumptions and guarantees would someone like to suggest a possibility for the system specification? So first, is this sufficiently clear, right? We are taking a component M with a specification C and component M prime with specification C prime, okay? So our problem is to compute the specification for the system, right?
I'll give it a try if nobody's trying. I'll be the one.
Okay, great, thank you.
So
interactivity here.
Yeah, I love this. Okay, so I think the composed specification is that as long as I is less than 1, then O prime is equal to I.
Okay. So that's exactly what the agreement seems to be, right? Something like this. Could you, Andrea, tell us a little more? Why did you say that the system should be I less than 1? Instead of I less than 2, which is what this guy has?
Well, so So it's a bit, so there is a notion in programming languages of what it means for behavior to be undefined. So I was thinking in that same way. So I know that if I know that I need to say something about O prime, right? And to say something about prime, I need to use C prime. And now I know that I cannot say anything if O is not less than 1. Okay. So I remember, we'll go now left, right, and look what's below. What can guarantee me that O is less than 1? And I look at the constraint and I say, well, actually, O is going to be defined for all the i's less than 2, but I need that less than 1. So I said, well, then I less than 1. Then I went forward and just said O prime equal O. So just identity. But I see that there is like a question mark after my answer. So now I wonder whether it's correct or not.
Oh no, the question mark here was meant as is this the reasonable specification? So, but I completely agree with what you said right now.
Okay,
so,
okay.
Yes. So I would like to make a couple of additional remarks about the virtues of this specification. Virtue number 1 is what you stated. You said the reason we have here I less than 1 instead of I less than 2 is because when you make I less than 1, you meet the assumptions of your 2 components, right? So that makes sure that you are going to operate your system within the assumptions of the 2 objects, M and M prime. And the reason I would claim that is important, right, is because if you are putting a component in your system, presumably you want that component to do something, right? I mean, you don't just put a component for the heck of it. So as a result, we should operate everybody, all the components within their assumptions. So that's the reason, that this guy is less than 1. The other virtue of this specification is that assumptions depend only on the top level inputs, and the guarantees depend only on the top level inputs and outputs. In other words, our internal variable O completely disappeared from the system level specification, right? Which is what we want for a specification. Specification should only refer to the interface, right, of the component. So this is the system specification, right? Now, the question now is, okay, we discuss all this algebra of contracts and blah, blah, blah. The operation that should give us the system specification for using the contracts, the subsystem specifications is composition. But if you apply composition directly, you get a complicated expression that is much less intuitive than one we had before, right? So then the question is, how can we justify the simple result that we obtained, from this longer algebraic expression? So we're not going to to go into the details of this, but the point is that we can do a fair amount of computational logic in order to bring this composition operation into the form having the virtues that we stated before. In other words, assumptions only apply to inputs, guarantees only apply to inputs and outputs. And using the tool that I mentioned before, using Pacti, this is what this example would look like. Okay, so we would declare 2 contracts in lines 1 and 8. Let's pay attention, or let's take a look at contract 1. We are defining a contract with input variables I, output variables O, assumptions input less than 2, guarantees output equal to the input. Okay, and for contract 2, we do a similar one-to-one mapping of what we saw before to what we have in Pacti. So to Pacti, we say input variable is O, output variable O prime, and so on for assumptions and guarantees. Then, if we ask the tool to compose contract 1 with contract 2, the result that we get is shown in the slide. So the tool says exactly what Andrea pointed out. Your top level input is going to be I, your top level output is going to be O prime. These are your assumptions and your guarantees. So what Pacti did is that it eliminated, right, that internal variable that we were discussing earlier. So this is the notion of composition. And we have an analogous situation here with quotient. So in the case of quotient, this is the setting. Suppose that we want to build a system M, okay, with input I and output O prime. And in order to implement it, we are going to use M prime. M prime has input I and output O. So the question that we want to answer is, what should be the specification of this missing object? Question mark. Okay. So just as before, we have a specification C for the top level, and we have a specification C prime for our existing component. Okay. And again, we can brainstorm what would be a reasonable specification for this missing component. In our experience, it's considerably less intuitive to nail down by, in a few seconds, what should be the specification of this missing object. But if we take the time, we would reach to an expression that more or less looks like this. The input O of this object, as long as it is less than 2, O prime should be equal to O plus 1. Okay, so in this case, what we are finding is this missing specifications, and I am going to skip the details as before. Again, this is the expression that we would obtain by simply plugging in the specifications into the algebra, but we do a fair amount of computational logic in order to come up with an easy answer, with an intuitive answer, right? So assumptions, input less than 2 guarantees this arithmetic expression. And again, if we use Pacti, there is a one-to-one mapping between the previous slide and what we give the tool. So in the case of Pacti, here we would say our top level specification is given by this. Our existing subsystem specification is given by this. We take the top level specification, we quotient by the existing specification, and the tool tells us what is the specification of what we are missing. Okay, so this is what we have implemented right now, and I would like to ask, what is our time looking like? I know that we are getting close to 5. Do we have about 10 more minutes, or just let me know what is our?
I think
we can have them
before. Yeah, sure.
Like there's
okay.
there's no room to leave, right? That's the beauty of Zoom.
Okay. Okay. So let's see, what we have next is various case studies, in which we have applied these specification-based approaches in order to understand, what would this look like in, things like, self-driving cars or synthetic biology. Actually, synthetic biology has been a very fruitful subject in which these ideas have found application. And we have also applied this to the design of space missions, and NASA Jet Propulsion Lab has been leading that effort of applying specification-based design to that. So let me give you an idea, right, of the types of questions that we have been trying to address using this tool and methodology. So in the case of autonomous systems, this is what we have in mind. So take a look at the diagram that we have on the right-hand side of this slide. So on the right-hand side of this slide, we have a vehicle that is approaching a crosswalk. And then in the crosswalk, we can have a pedestrian, or we can have an object that is not a pedestrian, or we can have nothing. So the crosswalk may be empty, okay? And we model the vehicle as a system that just consists of 2 pieces. So piece number 1 is there is some sort of perception component, for the vehicle. And the second component of the vehicle is a controller that has to satisfy some safety property and also some liveness property of making sure that there is progress. So, okay. So, oops. Yeah, do you see my mouse? I think you see my mouse. So I'm trying to point out that this CSIS specification. So our impression is that generating a specification directly, a formal specification directly for a perception component is not the most intuitive, task in the world, right? Because the way in which we are generating, in which we tend to generate specifications for perception components is using confusion matrices. So, if we're not familiar with that, a confusion matrix is effectively the true positive and false positive rates that our classification has for the perception component. So, coming up directly with a confusion matrix is, again, not intuitive. So what we are doing is that we are beginning this by saying, let's provide a top level specification for our car. And the top level specification looks like this. We are saying, our assumption is going to be that this D, which can stand for visibility, that the visibility of the environment is bounded by some numbers. So high visibility means we are in good environmental conditions. Low visibility means it's raining a lot or who knows what. Right? And then the guarantees that we want the top level system to have are split in 3 pieces. But the short story is that each of these constraints G here states a lower bound on the probability of satisfaction of a certain safety property. Okay, so we want to be safe, and we have 3 controllers that are going to be saying what does it mean to be safe if there's a pedestrian, some object, or when it is empty. Right, and this is the definition of the G's. The G's are, we are imposing a lower bound on the probability of satisfaction of that safety property. Notice that the lower bound is an affine function of our visibility. So we are saying, okay, if visibility is excellent, we are going to require you to be safe with extremely high probability. You are going to have some leeway if it is not, if visibility is not very high. So that is for the system. Okay, the system says, I want you to be safe. Okay, and then we write a specification for the controller. Okay, so that's the CC and that we see in this slide. And the controller is going to say, okay, I am going to place a bound on the probability of satisfaction of my safety properties as a function of my true positive rates coming from the perception component, right? So if the perception component is very confused, there is no way the controller can do a good job. If the perception component is right on target, then the controller should ensure that we are safe with very high probability. Okay, so again, at this point, we have a specification for the top level system, and we also have a specification for the controller. So using that data, we can use the notion of quotient in order to derive a specification for the perception component. And the specification that we compute via quotient is going to make assumptions on the visibility in the environment, and is going to make guarantees on the confusion matrix of the perception component. Okay, so one of the attractive aspects, I would say, of this methodology is that what we can do at this point is we can hand the perception specification, to an expert in perception, and as long as that person implements a perception mechanism that satisfies the specification, we know that the system is going to satisfy its top-level objectives. So in the next slide, what we have is the actual numbers, but I think that the idea is already there. So this is how we computed these numbers and so on. So that's an application, right, that we did to this self-driving vehicles. Let me go to synthetic biology. In synthetic biology, it was a similar approach of finding missing components via composition and of generating compositions of components to understand what a system does. So let me go first to the system being built. So there is a project right now involving Caltech and other institutions in which the objective is to modify the rhizosphere of a plant. So the rhizosphere is the ecosystem surrounding the roots of a plant. So the idea here is to modify the genetic circuits of bacteria so that the bacteria generates an output that the plant is going to catch in its roots. That output is going to travel through the plant, and eventually there is going to be an observable on the leaves of the plant. Okay, so that is the system view, and our design problem happens to be inside of this bacteria right here. So we understand the bacteria as having several components. So in this case, is a couple of sensors and some logic internal to it. And then the application of the methodology that we have been discussing was as follows. We had specifications for 2 of the components, for the DNA assembly sensor and for this repression mechanism. And then and we had access to a library of sensors here for this DNA assembly, for the XRFP component. The idea here was that we had to choose a sensor that was going to allow the system to work. So considering that we had a library of components, we generated contracts for each element in the library. And when computing contract composition, sometimes Pacti is unable to eliminate an internal variable. So what that means is that the guarantees of that component are not sufficient to satisfy the assumptions of another component. In other words, the system is going to be faulty if we choose that component. Right. So we use composition in order to prune, we could say, our library and only select those sensors that would yield a valid system. So that was what we could call application number 1 of this methodology. And application number 2 was as follows. So in application number 2, we had experimental data for the entire system. We also had data for the 2 sensors that we are using in our system. Using the top level specification and the data for the sensors, using the quotient, we were able to characterize the specification of the internal component of this repression mechanism. Now, that proved to be quite useful because measuring the internals of the bacteria was extremely difficult for our experimentalist colleagues. The next thing that we did was we modified one of the sensors that we had in the system. We chose another one using the previous model that we computed for the repression mechanism. We could now predict what would happen in the circuit, right? And we found out that the methodology had predictive capabilities, right? So this is now being tested in some experimental settings, right? So yeah, this was a second application, we could say, of this contract methodology. Okay, in signal processing, okay, we have a similar situation of finding missing objects and so on to build systems. I would like to, let's see. Okay, so let's go to conclusions now. So in the end, what do we gain by talking about contracts? So we think about systems and the subsystems in terms of their specifications, right? Not their implementation details. There is a time in the design process in which we do not yet have access to detailed models of our components. So at this point, a specification-based approach would allow us to make design trade-offs between components. So this is typically a task that someone with the title of chief architect or principal engineer would undertake at a company, right? In which they take a high-level objective and they split tasks among multiple experts. Something attractive about this is that the conclusions that we reach by reasoning exclusively on specifications are going to hold for any implementation that adheres to the specification. So the idea is that after you do a breakdown of a system specification into subsystem specifications, we are now free to implement the subsystem specifications in any way we want, right? And we know that the result is going to, the result of our analysis is going to hold. Something else about contracts is that they make assumptions first-class elements of the theory. So we have to explicitly state what are the assumptions for all components. In many times, what we find is that assumptions are forgotten as we are detailing what a system does and so on, but contracts do not allow us to do such a thing, right? In our experience, assumptions tend to be considerably less intuitive than operating on guarantees. And we have seen that in many examples. So, okay, assume guarantee reasoning, and in this case, enabled with a software tool like Pacti, can really help us to scale compositional reasoning to large designs. The algebra has many design relevant operations, right? And then the last point should be a bit of a warning that what contracts give us is logical assumed guarantee reasoning capabilities to do system design, right? But they will not add anything to our analysis capabilities of components. So if we want to analyze a component in isolation, we have to apply the tools that are proper to the design discipline in which we are imbued. So if we are doing control, our control tools or our security tools or our tools from any discipline. And thank you so much. This was the content for today.
Thank you so much, Inigo, for the very nice presentation.
My pleasure, Nicholas.
Are there any questions?
I have one question.
Absolutely.
Please go ahead.
Thank you so much for the talk. I just randomly saw this on Twitter and then thought it was really interesting, stayed around. I was just taking a look at Pacti. So what's the kind of limit of number of components that you could implement with Pacti?
Okay, let me go to the Pacti website actually. Yeah, Salim, as was hinted during our conversation right now, one of a very central concern in the development of Pacti was to make it fast, right? So, because one of the main use cases that we see for such a tool is to enable, design space exploration, right? So, in the case of design space exploration, we want to somehow understand how various choices in our design would impact the top-level system and so on, right? That being said, let's see. We are. Can you confirm we are seeing the Pacti website on the share screen? Do we see?
Yes.
Okay, good. So the reason I wanted to point it out is because if we go to the top, there is this case studies link, and under the case studies link, you see some of the applications that we discussed right now, right? But if we click on any application, and on the right hand side, we have this GitHub icon, so you can see the entire code for each of the applications. The application that we did to space missions, has a significant amount of benchmarking here. So the space mission case study was led by NASA, and I will tell you a little bit of what they did. But first, I'm going to answer your question about numbers. So the number of contract compositions that NASA was able to do in order to do design space exploration was on the order of 60,000 per minute, using contracts that had, if I'm remembering correctly, going from 6 to 15 variables and so on. So, in other words, they were able to explore quite a significant amount of space. So indeed, efficiency has been a very important concern, right, for the development of Pacti. To a certain extent, Pacti sometimes is sound but is incomplete in the sense that you are always if it gives you an answer, you're going to get an answer that is correct. But we sacrifice some completeness for efficiency. We thought that that was very much needed. So sometimes Pacti is going to tell you, I don't know how to do this, but it doesn't mean that the solution may not exist. Okay, but does that answer, Salim?
Yes. I mean, just to kind of follow up, I don't know if anybody else has questions, so I can also stop. But I mean, the way things are presented are, I guess, super abstract. I think one area that if you could probably elaborate a little bit more on is how could you translate the results from Pacti to kind of real world applications? Like the way you explained the battery example and the voltage in the camera, I think made sense. But for like a larger system, so like what systems were they looking at here in the space mission design space exploration example? Like I'm currently looking at a design space exploration problem, but I'm taking a totally different approach, and I'm trying to think about how to maybe try to apply these tools. Okay, so let me give you an overview then of what is going on with this design space exploration case study.
in this picture that we see in the website, the mission consists of the following scenario, right? So here we have Earth, and here we have an object that we wish to study. And then this is an asteroid that tends to be called an SBO, a small body object. So the idea here is we are going to send a spacecraft to take some scientifically relevant measurements out of this asteroid, okay? So the spacecraft that we are sending consists of various modes of operation, okay? So the modes of operation are indeed 4, they are right here. So you have a mode of operation called DSN, which is communicate with Earth, right? So communicate with Earth means that you are the spacecraft, you are going to position yourself in such a way that you have a good line of sight towards Earth, and you are going to send whatever data you want to send, right? So that's communicate with Earth. Then you have another mode of operation called acquire observations. So that means that you are sufficiently close to the spacecraft is sufficiently close to the object that we want to study, and then it's going to take whatever measurements it needs to take. This next step right here is this trajectory correction maneuver. So what can happen, right, is that when you point yourself towards the Earth in order to send data, or when you point yourself towards the sun in order to charge your battery, right, you are probably getting farther away from the object that you want to study, right? So sometimes you need to correct your trajectory in order to approach the object under study so that you can take the measurements. And charging, I think it's fairly obvious. That means you put your panels. So I am mentioning this because what we did in this situation was to model the entire mission as a sequence of modes of operation of the spacecraft. Each mode of operation of the spacecraft was characterized as a set of contracts that I will show you very soon. So every mode of operation had assumptions on the amount of battery charge that you had to have before you engaged in that mode of operation, and it also had as an input the duration for which you were going to be in that mode of operation, right? And then the guarantees were what is going to be your state of charge after you are here, what is going to be the amount of scientific data that you have, after so much time here, and so on, right? So what we did in this case was that we generated an entire sequence of modes of operation, and then when you do composition of all these modes of operation, you get an understanding of what your entire mission looks like, right? So you say, okay, if I compose 20 modes of operation, I know that I am going to satisfy my objective of gathering so much data that the scientist told me that I need to gather, right? Or that I want to make sure that that my battery never falls below a certain number, and so on. So these are the high-level views on the modes of operation. Now, if you take a look at any of these subsections on the left-hand side of this website, if you look at something like the power viewpoint, okay. So the power viewpoint means that we are focusing on writing a power specification for each mode of operation. Notice the methodological advantage that we get from that, right? So this is just a high-level definition, what is being shown here. But let me, okay. So actually, let me go here. So a methodological advantage that we have with this is that for every mode of operation, we can write multiple contracts, each of them applying to different aspects of what we care about. One aspect of what we care about is power. Another aspect of what we care about is scientific data gathering. Another aspect of what we care about is how close we are to the object that we need to study, right? So on the left-hand side, you are going to see how we specify all these different viewpoints or aspects of the design, right, for each mode of operation. And then we use the composition operation in order to understand the entire mission. After you compose 20 modes of operation, the contract that you are going to get tends to be pretty big, right? Because now you have state of battery after the first mode of operation, the second, the third, all the way to the 20th, so you can get a very lengthy object. So what we did at that point is that we query the resulting specification using optimization. So we start asking questions like, tell me what is the minimum value that my battery charge is going to reach in the entire mission. And then you can say things like, you know what, I don't like that. I don't like my battery falling below 30%. Therefore, let me add additional constraints that are, let's see. Okay, therefore, let me add additional constraints that are going to force Pacti to find restrictions on my durations that never allow my battery to fall below this number. Okay, so regarding your question about what kind of output do you get at the end, in the case of the space mission, we got a large specification that we queried using optimization. Okay, does that make sense?
Yes, very, very helpful. Thank you so much.
Oh, okay, excellent. No, my pleasure. And again, all details are here, and yeah, please feel free to let us know if there are any questions.
I don't know if you're open to sharing contact info, maybe I could try to follow up later.
I guess
if you're okay.
Yes, absolutely, absolutely. Here's a chat. So I am writing my email address in the chat.
Great. Are there more questions? Okay, if not, thank you so much, Inigo, again for a very nice presentation. And thank you for attending, and see you next week.
No, thank you so much to everyone. Hope you have a good rest of your day.
Bye. Thank you.
Bye-bye. Bye-bye.
Thank you.
Thank you.